Please join me in welcoming to the Distinctive Voices podium, Dr. Fran Bagenal.
Good evening. Great pleasure to be meeting with you this evening, and talking about the approach, the very last phases as we approach Pluto after 9 years on our way to get there. We're very close. We're nearly there. So I'm going to talk about Pluto, why we care about the outermost parts of the solar system, what we're going to see, we think when we get there, maybe, and so on. So let's start off with talking about the solar system a little bit. And we all know, using our own favorite acronyms involving pizza pies and things, Mercury, Venus, Earth, and Mars, which are the small inner rocky planets. Then we have our giant outer planets, Jupiter, Saturn, Uranus, and Neptune. And then things get a little bit more complicated. We have the asteroid belt of small objects between Mars and Jupiter. We have Pluto in the outermost part of the solar system, along with now what's called the Kuiper Belt, named after a Dutchman, Gerard Kuiper. Kuiper rhymes with viper, that's the way I remember. But the point here is that we have, I don't want to get into definition of planets. To me, what's more important is the fact there are words in front of the word planet. Small, inner, rocky, giant, outer, gassy. And we're going to talk about dwarf planets later when we get to Pluto. So in fact, let's start straight away with Pluto. In 1930s, Clyde Tombaugh was a young man working in the fields and wanted a job in the 30s, so not a time when it was easy to find work. But he was a very good, amazing eyesight and keen astronomer, and he went to Lowell Observatory in Arizona using this telescope here, which you can go visit and see, by the way. It's still up there. And he spent his nights taking photographic plates and then comparing them during the day, processing them in the morning, and then looking at them and trying to look for objects that move relative to the stars. So you can imagine that this was really quite difficult doing this night by night, looking and comparing. So he had a means of blinking between the two plates and looking for something that was moving relative to the stars. And he found Pluto in 1930. Now, not a whole lot happened in the outermost part of the solar system until this person, Christie, was actually trying to work out better data for the motions of the planets, and in particular the motion of Pluto. And so he took this picture, and the one on the left you can see is Pluto, and because of the Earth's atmosphere, small, dim objects look really fuzzy because of the Earth's atmosphere, even with a good telescope. But you can sort of see that on the right, this blob has a bit sticking out of the bottom, and that, he noticed, came and went on a time frame of about 6 days. And he realized then that this was a moon, the moon Charon. He called it Charon, partly because of mythology, but also because of his wife, who was a Charolyn, similar name. And so we now had a Pluto with a moon. So Pluto is out beyond the orbit of Neptune, mostly outside. It spends a little bit of time inside the orbit of Neptune, and orbits the Sun every 248 years. So it's not been even halfway round since it was discovered. And you can see from these dates here, a lot has happened since it was discovered in 1930, but it's moving very slowly, even when it's closest to the Sun. Okay, so since this early discovery, we've now looked at the outermost part of the solar system, and we can use modern technology to really speed up the process. And so instead of using photographic plates, we use basically the same sort of technology that are in people's phones. You have a digital camera at the end, and what you can then do is put this into your computer and make the stars static and see if you can find things that blink, as in this case, or move, as in this case. And now, since the second Kuiper Belt object was discovered in 1992, we've found thousands of objects here in the outer solar system. So it's not quite as many as the 250,000 we have in the asteroid belt, but a lot of objects out there of all sorts of sizes and shapes and so on. And here is a movie that has been put together by Alex Parker, which shows Pluto moving, but you can maybe see, especially if they dim the lights a little bit, you can maybe see lights. These are discoveries over time, and you can begin to see surveys that were made in different directions. And then the larger objects are the larger Kuiper Belt objects that were detected. I'll show you some of these. But you can see they're moving quite slowly with Keplerian motion around the sun. And then when you tip the whole system on the side and look at the ecliptic plane, the plane of the planets on a side, you can see that these objects are actually scattered out of the plane of the ecliptic. They have not only elliptical, somewhat eccentric orbits, they also are tipped out of the plane. And so they're scattered. They've been scattered as they were formed. So what do these things actually look like? We've been able to use spectral analysis to get a sense of color and also a little bit of composition. And you can see there's a whole range of different colors. They have great names like Quawa and Haumea and Make and Eris and Pluto. And you can see, actually, they also have moons. This is Charon and the moon Pluto. And these are various ones that we have. And to the same scale, we take the largest asteroid, Ceres. Here's to scale. I've blown it up a bit here. And this is the asteroid that the Dawn spacecraft recently took a bunch of spectacular observations. This is taken by the NASA's Dawn spacecraft. And you can see, by comparison, these objects in the outermost part of the solar system are actually a little bigger than the objects of the asteroid belt. And they're very varied in shape, in size, in color, which tells you something about how the icy surfaces have been processed in different ways. Now, for a long time, a lot of people thought that Pluto was an escaped moon of Neptune because, indeed, Pluto's orbit does go inside the orbit of Neptune. And I remember at the University of Colorado, we celebrated Pluto's perihelion. In those days, we could drink a keg of beer. We were not allowed to do that on campus anymore. But back then, we celebrated Pluto's closest approach to the sun. It's since moved out beyond the orbit of Neptune. And people thought that it must have been a captured moon. Well, we actually now know that if you make this funny diagram where you keep Neptune fixed and you allow the other planets to move, and you look at Pluto's orbit, which is the outer one, it never goes close to Neptune because there is a resonance between these orbits. And so Pluto goes around the sun twice for every 3 times that Neptune goes around the sun. And so, indeed, you'll see here that Pluto, in fact, gets closer to Uranus than it ever gets to Neptune. So it's in a safe orbit, as are many of these other objects that are out there that I showed you in that movie, where it's been scattered out into a safe orbit that is not going to get captured by Neptune. Unlike Neptune's moon Triton, which is a captured object. So we think these objects are old icy objects from the earliest part of the formation of the solar system. Some got captured and some were scattered outwards. So they do this dance, but they never get close together. So let's think about what the size is of these objects. This is to scale Pluto and Pluto's moon Charon. It's actually the largest sort of combination of a moon and a planet. It's almost a binary system. And for scale, we have here the Earth. So you can see, quite small compared with the Earth, but they're really quite close. And of course, on this scale, our moon would be about a quarter of this size, and it would be 60 times the radius of the Earth away, so way out in the other room. So let's think about what happens with Pluto and Charon orbiting each other. And to do that, let's think about our familiar moon. And we all are used to looking up and seeing this face of the moon. the same face facing the Earth, just the illumination changing over the month. And so we have a situation, another resonance, where the moon spins once for every time it orbits the Earth, and so that keeps the one face facing the Earth. Now, with Pluto and Charon, we have an interesting situation that they're in a tighter kind of resonance, where both Pluto and Charon both orbit each other every 6.5 days and spin every 6.5 days. And so they keep facing each other. So I put people on here, and you think about what it would be like to be a blue person on Pluto looking up, and what would you see? Well, you would always see Charon in the same place in the sky. So think of the sun coming in from one side, then you can see that they're going to go through phases. They're going to go through full and quarter and new and so on. But they will always be in the same place at the sky. And then think about what it would be like to be a red person. You don't see anything. You don't know from this diagram, right? You wouldn't see the other object. Okay? So I think that'd be a great story for a science fiction story. Anybody wants to write a science fiction? I think that'd be great. Cool. So this is a spin orbit. These are phase locked, and so they keep facing each other. Now, Pluto is tipped on its side, and so at the time when we first started making observations of the system, actually more in the 80s, when the telescopes got better and they got a little closer. At that time, here it is orbiting around the sun, and here we have it spinning with Charon going. And in fact, if we make a movie of this, you can see that Charon is moving in front and behind. Now, we also, you will see, is that Pluto is moving. And this is because the center of mass of the system is actually outside Pluto. It's a little towards Charon. And so they both orbit around this center of mass, this barycenter, around each other. And remember, because they're facing each other, they're locked in this spin-orbit resonance, it's actually very much like this system that I have here, where I just have a Pluto, slightly bigger, about twice the size of Charon. I found the balance point, which is fairly close to Pluto, so it's actually a little denser than Charon. And then you can see that, in fact, the system is very much like this. So at this time of the 80s, it was tipped on its side like this, with the sun coming in like that, okay? And then over the seasons, as the system moves around the sun, later, a quarter of a orbit around, it'll be sideways to the sun, going around like this, okay? So the time when we were observing this system back in the 80s was very convenient, because this moving in front and behind of Charon moving in front and behind allowed us to use these what we call mutual eclipses to measure the dimming of once one goes in front, you dim the total light coming from the system. Once it goes away from each other, it brightens up again. And so by looking how Charon moves in front and behind, and then, of course, this varies over time between 1985 and 1990, we were actually able to map out the surface lightness and darkness a little bit, okay? And we add that with the very best pictures from Hubble, it's barely resolved. We're talking maybe 20 pixels across Pluto. This is the best we can do from Earth, either Earth orbit or from the ground. And it's slightly orangey. We've got black pieces. We've got white pieces. But, you can't exactly see canyons and mountains and features, right? That's the best we can do. So just to give you a sense, here is an object that you're probably very familiar with. You've seen pictures of this. It's a planetary object. Anybody want to shout out what they think it is? Indeed it is. Okay, on the same resolution. Okay, let's do another test. What do you think this is? It's a painting. A famous painting. It's the Mona Lisa. Right, okay? So, you know, when we look at this picture of Pluto, we're seeing a very fuzzy object, right? I mean, it's we see these little squares and you think it's resolved that well, but it's not really. It's a little exaggerated. So we have here Pluto and Charon. Pluto is indeed a little orangey compared with Charon, which is a much more sort of gray, black and white. We don't know what those colors are, but it could very well be either sort of dirt, that is rocky pieces, dust, or broken up asteroids that come out and hit the surface, or it could be being out there, an icy surface, being bombarded by energetic particles, charged energetic particles, over a long period of time, that you convert things like methane ice and CO2 and CO and things like that into very primitive hydrocarbons on the surface. We don't know what the brown stuff is. But we do know it's very cold, and it really doesn't matter whether you use Kelvin, Celsius, or Fahrenheit, it's extremely cold. And so we know that water is frozen really solid, and then we also have on the surface frozen carbon monoxide. We suspect there's also carbon dioxide. We've detected frozen nitrogen on the surface. It has an atmosphere of nitrogen, but mostly these things are all ices on the surface. So we know it has an atmosphere because a very clever chap, Jim Elliott, used a telescope in a plane, the Kuiper Observatory, Airborne Observatory, and worked out there was a time when a star was going to move behind Pluto. So, you know, you observe Pluto as the star goes behind. It's actually the Earth moving relative to Pluto that's causing this apparent motion of the star. But if you're looking at Pluto, you see the star dim out and then come back in. And if we look at this is starlight now as a function of time, it dims out and then comes back again, right? Now, if there was no atmosphere, it would just blink out and blink back up again. This would be a vertical line. But in fact, it has a slope to it, and from that we can derive a density and temperature of the atmosphere. And we're talking microbars, so the atmosphere that we're breathing here is roughly 1 bar, and so it's a millionth of the pressure in this room. It's the same gas, it's nitrogen, N2 mostly, very little oxygen, mostly N2. But it's a low pressure, and indeed the temperature is low. So this is basically evaporation, sublimation of nitrogen ice from the surface. Now, in fact, we now believe that this atmosphere is escaping, flowing away from Pluto. Pluto's gravity is relatively weak compared with the Earth's, and so the atmosphere escapes. And so the top of Pluto's atmosphere is actually, we think, maybe half the way to Charon's orbit. And so comparable to the scale of the Earth, it's sort of the same size as the Earth with the Earth's atmosphere on the outside. The Earth's atmosphere is much more tightly confined to the planet, but in absolute scales, they're similar. So we think that over the age of the solar system, so if the escape of the atmosphere has stayed pretty much the way it is now, then we will have lost maybe 1 kilometer of ice over time, which is significant. It's not enough to remove or make Pluto shrink significantly, but it's enough to sort of affect the geology of the surface. So what happens when the solar wind, the charged particles coming from the sun, impacts this atmosphere, and what happens when the solar photons, the UV light, ionizes this gas? Well, we think what happens is there's something that works a bit like a comet, where the charged particles of the solar wind carry away with them the ionized atmosphere. But I'll be honest, we can make these computer simulations, but it's complete guesswork. We don't know. So then let's think about what the surface of Pluto might be like. So we'll use Neptune's moon Triton. That was that captured moon. So maybe they came from the same population early on. And what you see is an icy surface. So this is the Voyager picture that was taken in 1989. I think it was about September 1989. Flew by, took these pictures. And we see a very strange, it's called a cantaloupe terrain because it sort of looks a bit like a cantaloupe. But it's ice that has evaporated and condensed and maybe been pushed around by motions inside. We don't really understand. But what was very interesting and very surprising was that there were actually plumes and there was sort of oblique view. So we're pretty sure this is a plume of black soot-like stuff that comes out of vents, which is very surprising because it's very cold. It's hard to imagine how this works. But maybe you have a layer of ice that the sunlight can penetrate and heat up the stuff underneath, and that bursts through. So, this is an artist's conception of what these plumes might be on Triton. And who knows, maybe we'll see this on Pluto. We have some idea of the interior. We know from the density it's sort of half rock, half ice when we look at Pluto. It's possible that there may be a layer of water, but I think it's probably ice, mostly pretty frozen, a very thick layer here. We are pretty certain that it's big enough that it did melt earlier on due to short-lived radioisotopes early in the solar system, so it probably did melt, and the heat of formation as well meant that you separated out the rock and the ice. But when we look at Sharon, we don't know whether it sort of remained fairly uniform mixture of rock and ice, or whether it also separated out with the denser rock going to the center and the ice on the outside. We don't know, and maybe we'll be able to find out. So this, again, is wild speculation. So, before we get on to the New Horizons, I want to have a quick time out to talk about why. Kids get really excited about Pluto. They all love Pluto. They all, got very upset when it was demoted and things like that. But to step back from that as an adult and think, well, why should we as taxpayers be exploring this part of the solar system? And why do we care intellectually about what's happening there? These are just chunks of ice out there. Well, the thing is that it actually gives us some clues about the formation of the solar system, how the solar system formed. We know that solar systems form from gases that condense and form a big cloud that then condenses down to make planets, star at the center, planets on the outside. And we've developed over the years a fairly simple, straightforward story of having a sun develop at the center of this collapsing nebula. It begins to spin up, it forms a disk, and that at some distance from the center, it cools off to the point where ices can condense. We have a frost line, and beyond that, we have ices, mostly water ice, but also ices of methane and CO and nitrogen and so on. And inside, we have rocks and metals. Now, by looking at the sun and by looking at these clouds at different places outside our solar system, we get a sense of the composition of the solar system, and that tells us that there are, in fact, relatively small amounts of rocks and metals. So not surprisingly, you're going to make small planets in the inner solar system. But there's a lot of ice out there, and there's a huge amount of hydrogen. So making small rocky planets is going to be in close to the sun, where there's only rock and metal can condense. And then these giant planets, we're pretty confident, are hydrogen being pulled into a icy core that's at the center. So the icy core could be something like 15 to 20 times the mass of the Earth. Right? So that's a huge snowball. And once something gets to be that big, it can pull in the hydrogen. And hydrogen being so abundant makes these big gas giant planets. Okay, so that's the basic story that intro astronomy has been telling for the past several decades. But things have started to get a little bit more interesting in the past, say, 15 years in our ideas of solar system formation. And that's basically because you can't really, with any sensible kind of solar nebula theory, make Uranus and Neptune where they are now in the time frame of our solar system, the 3.5 to 4 billion years of our solar system. So now these numerical modelers start putting into their computer, they make planetesimals, so that's sort of pieces that will become a planet, the building blocks of planets, into a numerical model that puts Jupiter, Saturn, Uranus, and Neptune in close. And I've been cursing my colleague that he stupidly chose blue for Jupiter and Saturn and red for Uranus and Neptune. He's a computer scientist. What do you expect? Okay. So he puts this in with a bunch of planetesimals and then lets the simulation go. And this is what you see. You scatter all of these objects over a period of a 1.5 billion years or something, and you end up, okay, I'll do it again because it's kind of cool. There we go. You can see Uranus and Neptune get scattered out by the big bully Jupiter. It's 300 times the mass of Saturn. 300 times the mass of the Earth, so 3 times the mass of Saturn. It's the big thing that pushes things around. And so you end up then with a situation where you have the giant planets had to sort of end up with where they're supposed to be, of course. If you don't, you just try your simulation again until you do. But you've scattered now these planetesimals out. So this is quite convenient. It can solve various issues. You can make Uranus and Neptune enclose in a reasonable time frame and scatter them out. We can scatter planetesimals into the Kuiper Belt. Oops, that's misspelt. And then you can also deliver water to the Earth, which is one way in which you can deliver water to the Earth. Okay, so this means then we're interested in going and exploring and finding out what Pluto is like, because it is, we think, an example of the building blocks, the planetesimals, from which the solar system was formed. Okay, those are the leftover pieces that didn't form the big giant planet. They just formed a dwarf planet in the outer solar system. It probably got scattered out by the gravitational interactions with the giant planets as Uranus and Neptune migrated out. So, time to find out what Pluto is really like. And so, back in 1989, a young, ambitious, just graduated student, Alan Stern, came to me and he said, hey, let's have a conference and then let's try working on a mission. So in May of 1989, we, group of us, we called ourselves the Pluto Underground. You know, we were young, yeah. Anyway, we had a conference, we wrote a book, we started campaigning to get a mission to Pluto. And to give you a sense of the time frame, the US Postal Service brought out these lovely stamps that had, you know, the exploration of Mercury and Venus and Mars and Jupiter. And poor little Pluto was not yet explored. And you can see how old this is because of the cost of the stamp back then, right? I mean, 29 cents, golly. Okay, so we proposed a mission. We wrote a proposal. We competed with another team to NASA. There was quite a lot of deciding how it was going to work and so on. But after a while, we settled down and we proposed in 2001. We won the proposal, and then we started building, designing, testing, and then shaking. You have to, if you want something to survive for 9 years, you've got to heat it up and shake it about and make sure that it's going to survive to get there. And so we designed this spacecraft. It had to be relatively small, and it's powered by plutonium-238. Here's their antenna, and then we have a bunch of instruments. And most of these are sort of cameras, looking at visible light, infrared light, UV light. We have particle detectors, PEPSI and SWAP, carefully acronym designed not to get the Coca-Cola company or the Pepsi company annoyed. And then we slapped on the back side of this spacecraft the most important instrument of them all, the student dust counter, which I'm very proud to say was designed, built, tested, operated, and the data analyzed by students at the University of Colorado in Boulder. And these students, in fact, here, Chelsea here is now a professional engineer in the lab and is continued. Most of them have continued in their career. It was the instrument that the only one that came in on budget and on time, and has been operating for the 9 years on the way out there. The way it works, this is a roughly life-size piece that has pieces of plastic, which when a piece of dust, because we're flying through the solar system that hit the piece of dust, makes a little electrical signal pulse, which then we count these pieces of dust that we ram into as we fly out. And we just like one a day, one every few days, that sort of frequency. And that tells us about the distribution of dust in the outer solar system that's made by the grinding up of pieces of chunks of asteroids and Kuiper Belt objects and so on. Okay, comets as they break up. And that's been working for the 9 years on our way out there, and produced a couple of PhD theses along the way. Okay, so after building the spacecraft, we finally put it on the top of a rocket. This is the Atlas V from the United Launch Alliance. It has a bunch of solid boosters on the bottom, solid rockets, and we slap on the sticker, and off we go. So,
we have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond. Plus 15 seconds. Everything continues to look good
after launch,
as the Atlas V vehicle climbs away from Florida's east coast. The 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
So, it's a relatively small spacecraft on a big rocket, and it left the Earth system. It actually flew past the orbit of the Moon in about 8 hours, compared with the astronauts taking 3 days. Right? So it was a really fast leaving of the Earth. It went out past Jupiter and got a gravity assist at Jupiter, sped it up a bit more, and then heads out past Saturn, Uranus, Neptune, and so on over 9 years. So you can go to the website, and this is off the website from today. So right now, today, this is where it is on approach to Pluto. It will arrive on the 14th of July. It'll fly past. It's a flyby. It's not going to stop. It's moving at 33,000 miles an hour. Okay? So, once you give it a kick, either from the Earth with a rocket or by going past Jupiter to get a gravity kick, because there's no friction in space, it just keeps going, climbing out of the gravity well of the sun, and will just go whooshing by Pluto. So we had to debate. We couldn't carry a rocket to slow down and stop. It's just too heavy. We would rather take science instruments. And so we had to decide, do we wait longer and move slower, which would allow more time to take observations, or do we just get out there as fast as we can and take the pictures as fast as we can? And we went with the latter strategy, which means it'll take a while to get the data back. I'll tell you a bit more about that in a minute. So when we launched, or just before we launched this, when we designed this spacecraft, there was Pluto and there was Charon. There are now 5 moons. So Hubble Space Telescope has observed not just Pluto and Charon, which are Pluto and Charon, right? This is where the spacecraft, where New Horizons is going to go through this plane. But now Styx, Hydra, Nix, and Kerberos are moons that are orbiting outside the orbit of Charon, so they're moving slower, and they're relatively small. They're not very well resolved by Hubble, but this is roughly the size of them. So if Pluto and Charon, compared with the United States, are about this size, then these are really pretty small. They're small objects. These are not large moons. And so then comes the question, if we believe that Charon was formed in the same way our moon was formed, through a big giant impact with the planet, then what were these leftover pieces, or were they later captured? The theorists, the dynamicists, are still struggling with how to make this happen. Okay, so we've talked so far only about observations that have been taken by the Hubble Space Telescope. Last week, we released observations taken by the LORRI camera on New Horizons, and this is the most recent observations that we've got. And maybe if I give you this example, you'll see this is Pluto zoomed in by a factor of 3, and if you have a little bit of a stretch your imagination, you might be able to see that there seems to be a variation in light and dark on it. It's still a fuzzy blob. We've got a ways to go yet. I mean, so we're getting there. We're starting to make these observations. But what we will get when we get there will be really quite spectacular. So we'll look at, as we go by, we go by in just a couple of hours and take these pictures, click, 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 as we go by. We won't be able to get both sides of the planet at high resolution, but one half we will get at a resolution of about half a kilometer per pixel. And so this is the moon at the same resolution. So we'll really be able to see things like cracks or craters or vents or, whatever we think of there on the surface. There will also be a few areas that we will be able to see in much higher resolution and get color pictures. So this is a picture of Europa, moon of Jupiter, and you can see, you're now beginning to see structures, in this case ice, and it sort of looks like icebergs sort of floating in the sea, but who knows what we'll see at Pluto. And then the best pictures, we will get the highest resolution will be about 70 meters per pixel. And so if we flew past the Earth and looked down on Manhattan, this is the resolution that we would have, comparable resolution. So you can see Central Park, you can maybe see some of the docks and so on. So, we'll get a good pictures of Pluto for one side, a patch of it, and then we'll get fairly low resolution for the rest of it. So there, now, what are we going to see? What do you think? I mean, the truth is, your guess is as good as mine. We don't know. And with just a few more weeks to go, and we will find out. We're nearly there. And, there are artist pictures that show things like the atmosphere and plumes and kind of geology on the surface and an impact crater, but we don't know. We really don't know. So this is we've not had a first exploration of a planetary object quite like this since Voyager. So 1989, it was quite some time ago when we last went for the first time past a new object. And so this time we will find out what this object really is like, which is exciting and fun. So thank you very much, and I'm happy to answer your questions.